Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome to episode 65 of the Reliability Matters podcast. This is part 2 of my conversation with Tim O'Neill of AIM Solder and Fred Dimock of BTU. On the last episode, we discussed solder voiding from a materials and equipment perspective. Today, we'll discuss profiling best practices. Tim O'Neill is the technical marketing manager for AIM Solder. Operating out of AIM's U.S. headquarters, Tim is responsible for developing and optimizing product and technical information, collaborating with complementary suppliers and equipment manufacturers, and ensuring AIM's products exceed expectations and meet market requirements. Tim is also a technical writer and presenter for industry trade publications and events. He has co-authored several papers on PCB assembly subjects. Tim is also an IPC-A-610 Certified Specialist. Fred Dimock is the manager of process technology at BTU International and recently started a consulting business, FCD-Global Services. Fred holds an associate's degree in mechanical engineering from Wentworth in Boston and a bachelor's degree in ceramic engineering from the State University of New York. Fred has also authored numerous articles on lead-free solder process control and operation of continuous furnaces. His papers have been published in English, Chinese, and German. He has taught numerous SMTA solder reflow classes and participated in the 5-45 subcommittee for the development of IPC-A-610 Reflow Oven Process Control Standard. Additionally, he wrote the chapter on solder reflow for the Handbook of Electronic Assembly, a guide to SMT certification by Dr. Lasky and Jim Hall. Fred received distinguished speaker status at SMTA Guadalajara, Mexico, and is a key presenter for the SMTA Jumpstart program for new engineers. This episode is available in both audio only and a video format. To view the video, complete with Fred's informative slide deck, visit our Reliability Matters YouTube channel. Now, here's part 2 of my conversation with Tim and Fred. Tim O'Neill, AIM Solder, Fred Dimock, BTU. Welcome back to Reliability Matters. Twice in a row.
Thanks, Mike.
And Tim, you now are the record holder. You've been on 3 times now. So congratulations. We'll put the trophy in the mail.
Oh, perfect. That's quite an honor.
It is. You've really established a high level in your professional career now.
Yeah, it's wonderful. I've made it.
Yes, exactly. Yeah, I'm sure somewhere on some street corner there's a star named after you, right? In the concrete. Yeah. Underneath all the gum and beer cans and all that.
Yeah.
Right? Well, welcome back. So we spent all of the last episode with you fellas talking about voiding mitigation, and where the conversation steered off to kind of toward the end was Fred's presentation talking about vacuum reflow, which is an amazing technology, very cool. And with vacuum reflow, and I've heard this not just from Fred, I've heard this from other experts in the field, that vacuum reflow is a great way to mitigate voiding, bring it down to either zero or near zero. Now, the world is full of mortals and superheroes, and I would think the superheroes with unlimited budgets are the ones that buy the vacuum reflow, for one project. But mere mortals may not have that same resource, right? We might be stuck using the standard convection oven, that we've been using for the last 20 years or so. So before we move on to our featured topic this week, which is profiling, kind of goes hand in hand with reflow. Before we do that, let's kind of wrap up the voiding mitigation discussion that we had on the last episode, where we talked about the advantages of vacuum reflow. So let's assume that the majority of the people listening to this don't have a vacuum reflow oven in their factory floor and aren't going to get one anytime soon. The mere mortals of the world, what do we do to within the scope of the oven or profiling? That could get us into profiling. Good segue. To reduce voiding. Now, we know from a material selection standpoint, obviously you want to go with a material selection with a flux that is engineered for lower voiding, obviously. I think you made a comment on the last episode that if you really want voids, you can certainly sell them a paste that's great voiding, right? If you really want a lot of voids. Considering most people don't, part of it obviously is proper paste selection, and probably the other part of it is oven settings, maybe oven brands, but we're not going to get into that, but oven settings and profiles and things like that. So let's kind of talk about, for the mere mortals that don't have the wherewithal to buy their way out of a problem, how can they take what they have and optimize it to the greatest extent to reduce voiding?
So as a rule of thumb, based on our experience in assisting our clients in profiling voiding out, it's not an uncommon request to ask, hey, can you help us? We have a component that's voiding beyond our customer's recommendation. Can you help us out? Generally speaking, a soak zone gives the volatile components in the solder paste the opportunity to evacuate the deposit, and thereby reducing the amount of outgas products that lead to voiding. I think I mentioned it in the last episode that solder paste is 50% flux by volume. So half of that deposit is flux, and it's got to go somewhere. And by heating it and getting those volatile components to outgas, that's the most common strategy. It's an input variable, and it can have an influence. It's not going to turn black to white, but it will. We can affect the results significantly, but not can't eliminate voiding altogether.
How much voiding can be mitigated by stencil design? I'm just thinking, for example, window painting or changes in the mask profile versus actual profile, heat profile on a machine. Is one more effective than the other, or is it a totality of all those efforts that provides the best results?
Well, there's a lot of input variables, and not all of them are well understood in terms of their influence on void results. Surface finish can have an impact. You mentioned solder paste chemistry can have a significant impact. Vias will have a significant impact. So we've experimented, and it also depends on which voiding you're talking about. Really, there are BGA voiding, which is an entirely separate, I think, thing than BTC voiding. So they're a bit different, and the mitigation strategies would be a bit different. But window painting, in general, reducing the solder volume to the lowest level you can and still get an adequate solder joint is a good strategy for void reduction in combination with reflow profiling. Those are two things that can be modified on a production floor. Like, we can't change surface finish, we can't change component finish. Those aren't luxuries that an EMS provider has. So what can he do? He can modify the stencil, and he can modify his profile. And those are things that we typically advise our customers to investigate. In fact, the new BTC IPC criteria came out last month. I think it's 7093. So there's some interesting information in there. It doesn't really give void reduction mitigation strategies, but it gives you guidance on other design criteria that might help the overall BTC assembly process. So that's certainly a resource that people should be consulting for guidance.
Who benefits most from lower voiding? Is it LED manufacturers or automotive specifically? You hear all these numbers that 30%'s fine. I've heard a lot of experts go, you can go 60 or 70%. It's fine for most mere mortals. But then there's people out in the fringes that can't do 3 or 4% voiding. That's too much. So is it the heat dissipation that drives the reduction desires to reduce voiding, or is it current flow? Is it mechanical bonding? What's the main concern when one is concerned about voiding? What do you think they're chasing there?
The thermal dissipation,
okay,
predominantly.
Yeah. And in the
Yeah,
LED world, that matters.
Yeah, but there are people now that work in high frequency that are looking at voiding in the leads because they think it affects that. We're hearing a bit about that, but I don't think anybody knows for sure yet. People are looking to do some studies in that area. We've supplied some samples to people that have very low voids in the lead area, and again, that's something that I think we're still learning about.
Yeah, I agree. Want to start talking about profiling?
Sure.
So here's a question for our experts here, and particularly for Fred, because when Fred's not on these podcasts doing his interview tour, he's home building machines, right? So as a manufacturer of reflow ovens, BTU in this case, I've always wondered, why doesn't BTU, I mean, maybe you do, but why are there third-party profiling companies like ECD and Kick and the others, which are all great companies? I've had Kick on this show talking about profiling. I know they know a lot about it, but they're connecting to your technology and in some cases, communicating and controlling your technology. What's the reason reflow manufacturers just don't make that part of the package where the profilers that are already in it, or do they do that?
The thing about profilers is that most of them can be either be run with wires, and the profiler stays outside the machine, and they've got these trailing wires that go through as it runs, so that the unit itself doesn't go through the oven. But the biggest thing is that they're able to put them in thermal shields, and those thermal shields allow the product, the profiler, to run through the oven with short thermocouples on it. Some of them actually have a radio link that goes to the outside, so you can see the profile as it's going through the oven. You can see it develop. Reflow, at least in our part, we do have built into the ovens, it comes as a standard part, a profiling capability, but it's without any of the radio links that you'll see. What it is just a plug on the outside, or a series of plugs on the outside. We plug thermocouples in that are very long, and they go through, and you can see the profile. Our high temperature ovens, we always use the onboard profiler to profile that oven, just because the profilers themselves will not withstand the temperatures or the length of time at temperature that we get into the high temperature ovens. If I've got an oven that's running 850 degrees C, for me to put a thermal barrier around that, it gets very large, and it gets large enough so it won't fit through the 2 or the 3 inch clearances, even the 1 inch clearance that we have, in some of those high temperature process pieces of equipment. On SMT, we have a little bit more, or I'd say that the guys like Kick and ECD, etc., have a little bit more analysis capability built into them. We could probably go and build those sorts of things into what we do, but these are something that's basically left with a specialist. Although we have discussed the opportunity to say, oh, gee, can we really go in there and build something that works better with our particular ovens and some of those, and that might be possible, but in general, no. Some of the nice things, though, about things like Kick and ECD, DataPack, is they can be configured to talk to the oven, so that you don't have to type in all the set points and do all of that work. It can do actually interface with our control system, so that the operator doesn't have to put the numbers into the Kick profiling system or the ECD. And after it does the analysis, it can actually have it automatically load the data back into the oven for the new profile. But it does not have a true interactive connection to say, oh, temperatures are changing in the oven here, and okay, so you're going to make a minor change in the set points. It doesn't do that. you really need to run it through with the thermocouples and do the profiling.
Yeah, excellent. Thank you, Fred. Tim, you still with us?
Yep.
Okay. Sorry to be
Throws it
ignoring.
off.
The danger in putting you off camera is I don't know if you'll be there when I bring you back. So thanks for sticking around. That's happened to me before. Obviously I cut it out, but I switched to guest number 3 or guest number 2, and when I came back to the big panel, someone's missing, and
I had to go to the bathroom.
yeah, I think nature called.
Yeah.
Anyway, I'm glad you're here. How much of the profile requirements is driven by flux versus the alloy? Is flux the main component that drives the granularity requirements of the profile? I mean, clearly you have to melt the solder, right? So obviously there is a metallic component there. But
that's a lead-in, right?
Let's.
Is that a loaded question, Fred?
Pardon?
Is that a loaded question for Tim?
Yeah, I think so.
Okay.
Well, I would say it is a number of things. Firstly, it is probably the entire assembly itself, meaning, look at it this way. If I'm hand soldering with wire solder, I don't need but 3 seconds to create a solder joint. Why do I have a 4-minute reflow profile? Well, I have a 4-minute reflow profile in order to accommodate the thermal mass of the assembly itself. So you got to get the whole thing up to temperature in order for the solder to reflow. So that's why things are the way they are. You don't need a 4-minute profile to create a solder joint. Maybe a few seconds. Instant, you can dip it into a molten solder, and the solder, you can create a solder joint. So that's why we have reflow profiles. It's to get this assembly up to temperature in a gradual way, so you don't thermal shock components, and everything has a chance to grow as heat energy is introduced. So further refining that, yes, the alloy certainly has an influence, and you have to eclipse the liquidus temperature of the alloy for, let's say, 60 seconds in order for the entire mass for all the solder joints to melt. So 30 to 60 seconds is usually our target to accommodate the alloy above the melting temperature of the material. But then the rest of the profile is to accommodate the flux. The flux chemistries, as Fred had mentioned in our pre-interview conversation, everybody's chemistries are different. And I would say that, as we have worked with obviously our own products, but we also work with our competitors' products, we've learned that different chemistries have different preferences, if you will. So competitor A might prefer a long cool soak to get better results, where AIM prefers a more linear profile with a minimal soak, and competitor B likes a high hot soak. And those trends tend to stick within product families. So you kind of learn, even by looking at a customer's profile, you can almost guess whose solder paste they're using just by the way that the profile is configured.
So flux is the driving factor, and that makes sense, particularly when it comes to no clean flux, because the idea of the way no clean flux is supposed to work is proper encapsulation, proper activation, even more so than other species of fluxes, and without that, you end up with a no clean that has to be cleaned if it's not properly profiled.
Tim mentioned something earlier that about 50% of the volume of the solder paste is flux, right? And the other 50% is the metals. Of the solder paste, of the flux part of that, the resins are about 50%, and then the solvents and other things that have been added to the flux, are about half. So about a quarter of what's in that system, by volume is the solvents and those sorts of things. And those are the ones that I think Tim will agree to this, but those are the ones that really drive what goes on in that thought set, in the profile itself, especially the early part, up to maybe I guess I'd say just under the liquidus. That's the one that really drives that.
Mm-hmm.
Our goal when we create a profile is to preserve the flux activator system as best we can until the actual soldering occurs. We don't want to deplete that flux by hitting it too early in the process and degrading the activator system before you get to liquidus. And that's where the difference between the families of products, between categories, so no clean and water soluble, and then it gets further broken down by manufacturers' design philosophy or engineering philosophy and the fluxes they create. But all of us create like a stepped approach. We have activators that kick off at 120C. We have activators that kick off at 170C. We have activators that kick off at 200C. And doing so, we make sure that we clean the surfaces and prepare them for soldering, and we also prevent reoxidation, because 4 minutes at temperature for those little pieces of metal is a lot of heat, and a lot of oxidation can occur. So we have to not only remove oxides, we have to prevent oxides from reforming during the reflow process.
Yeah, I was just talking to Phil Zaro, the consultant, and he did a whole lecture on flux exhaustion, which I think is what he called it.
Precisely.
Where it's just, it's done. It's done its job. It's kept the oxides off for as long as it can, and it's held the intruders at bay, the oxide intruders at bay, and then it just collapses, and the intruders come in, the oxides come back in and do what they do. So, I don't know how you guys formulate this stuff to last in that harsh of environment for that long a time, at that low solids content. I mean, it's amazing technology.
Well, and the deposits get smaller, and right. So now your available flux is less, and the mesh sizes of the powders that are used in the solder paste are getting greater, because we're going from a type 3 to a type 4 to a type 5. Some people are talking about type 6s and type 7s, which is right now the cutting edge of the technology. So this oxide layers, so the oxides only reside on the surface of the sphere of the solder paste, of the solder powder. And all of those oxides have to be reduced in order for the solder paste to coalesce. So this phenomena, and I can't stand the word graping, I prefer a non-coalescence condition, but I've heard the term graping because this uncoalesced solder paste looks like a bunch of grapes.
Yeah,
it's little metal balls that are all aggregated together. So you've got this. We're getting the squeezed on both sides. I'm getting squeezed because the deposit is smaller, so the amount of flux available is less, and the amount of oxide is getting greater because the surface area of the solder powder is exploding as mesh size drops. I mean, imagine a shoebox is your solder deposit, and you've got that shoebox full of golf balls with type 3, marbles with type 4, BBs with type 5, and dust at type 6 and type 7. So, and all that oxide layer has to be reduced. And profiling plays a significant role in how successful we are in accomplishing that. Not only do the chemistries have to evolve to accommodate that, but I know we discussed nitrogen. I think as the mesh sizes continue to get reduced, as the componentry gets smaller, nitrogen reflow is going to become much more common, because you simply can't accomplish with flux chemistry alone this flux exhaustion that you mentioned. We're going to need the extra reduction of oxygen in the atmosphere to minimize oxide formation.
With everything in life, there's cause and effect, there's pros and cons. So on the subject of nitrogen, I think I heard this, maybe I just had a bad dream and dreamt it, but you can confirm or deny. Where nitrogen can help mitigate voiding, it also increases the likelihood of tombstoning. Is that a correct statement? Or no? Well,
because wetting forces are increased by the absence of nitrogen, the forces can be applied to one end of the component. As the component gets smaller, now I have less mass, so it's more likely to stand up on one end because it requires less energy to get it to stand up. So pad design has a influence on it. Surface finish has an influence on it. Reflow atmosphere will have an influence on it. Yeah. So yes, all of those things have an effect.
Sure. So you go to nitrogen to solve or to mitigate one problem. you might have to make some
another.
mechanical pad design changes so that that mitigation doesn't create another problem. And it's just, there's never
Placement accuracy becomes more difficult, but now as the component is smaller, board
Right.
manufacturers have a bigger challenge because the pads are so small. Can they maintain the resolution that they need to when they actually build the board stretch? I mean, all of this stuff, as these things get micro miniature, all of these input variables become more critical. Everything has to just be more precise at every level.
Yeah. Fred, I cut you off. You were about to say
Oh,
something.
no. Yeah, there's a third thing that I hear about flux, and there are some people that want all the flux to be gone by the time you get back over to the solidus as you start into the cooling. That's just because they don't want a minimum amount of flux on the board when they get done.
Well, that's another issue.
So
That's, residue, controlling residue with no clean fluxes, as I'm sure you're aware, Mike, ICT becomes a problem with false opens for pin probing issues. So I don't want to step on Fred's toes too much, but I have this philosophy that the reflow profile is the only place in a SMT production line that that the outcome can be affected in real time.
Right.
Meaning, it is the only place I can make a change to change what's coming out of that oven, what's going to be different. If my printer is lined up properly, if my placement is lined up properly, how can I affect wetting, residue consistency, voiding? That's all in the reflow profile. So the importance of good profiling can't really be overstated, and it's often overlooked because it is a painful process. You know, there's best practice. Best practice to me would be, and it is very difficult for EMS providers, but you'd get a golden board with every SKU that you would thermocouple up, drill the underside of your BTCs, epoxy everything in, make it super nice, carefully arrange your thermocouples with Kapton tape so nothing binds or snags as it makes its way through the oven. And then you'd have that golden board to do your data collection. That would be ideal. That's not really how it works. And before the beginning of every run, you would take your golden board for said SKU and you would do your data collection, because not only do you want to generate the best profile, but you want to make sure that that profile is being run every time you run that assembly, because fans go out, heaters fail, birds build nests in exhausts. And so your reflow profile that you think you're running may not in fact be the reflow profile that you're actually running. So you have to do data collection at the beginning of every shift or at the beginning of every build. So, and when we're talking about the type of subtleties, increasing voiding, decreasing voiding, it becomes important to have that data available. Furthermore, if there is a reliability issue where a component has a premature failure, for example, or a push button failure where there's some sort of non-wet open condition, the first thing the client is going to say is, well, where's your profile? How do we know you didn't get things too hot? Or how do I know you didn't get things hot enough? So you need to do good housekeeping, good record keeping, and really run a profile at the beginning of every production run. That's best practice, but it takes time. It's not an income generator, and therefore it is often shortcut. And another common scenario is one profile for every assembly that gets run through the factory, just because it's such a painful task to run profiles as often as they really need to be run.
Yeah, that makes sense. You said it's not an income generator, but it certainly is a revenue retention technique. Right?
Well, it's an insurance policy.
Because everyone's job is to bring in money, right? You want to bring in revenue, and then you want to hold on to as much of it as you can, right? You know, and rather than it just going through a turnstile.
But you're not building boards, and as long as that oven's got a profiler in it, it's not generating revenue.
Right.
It's preventative maintenance. And it's a pain in the neck, and it takes time. You can't do the process any faster than the oven can run. You have to put the profiler together, run the board through, collect the data, analyze the data, make the adjustment, wait for the oven to change all of its settings internally, because it takes time if you want to cool that zone down. You got to wait 15 minutes for everything to stabilize and then run it again. It's right. It's unpleasant, but absolutely necessary. It's like going to the gym. You want a good result, you got to put the time in.
Yeah. Right. It's like a jet, wheels up time. Southwest decided that they would not charge for bags for the sole reason that when you charge for bags, people drag their bags on the plane and they can't turn their planes that quickly at the gate. And they realize that they make money when the wheels are up, but they lose money when the wheels are down, because the plane costs the same, besides fuel costs the same to lease, whether it's flying or not. So same thing with reflow ovens, right? You want to maintain them, you want to set it up, but you want wheels up time, right? You want boards running through it rather than wires and temperature sensors.
Data collection. Yeah.
Let's talk a little bit.
I wonder how Fred would feel about how. Because I'm not an equipment expert. I'd be interested in what Fred has to think. Are there things that oven manufacturers can suggest to make that process less painful and more productive?
That's a good question.
Yeah, I was going to say this. Maybe we shouldn't talk about profiling anymore. I mean, you've already talked about most of it, but there is something that can be done, that is being done on reflow ovens. And that is, once somebody has a profile that they're comfortable with, one that's the target for a particular product. And I agree completely that you should profile each individual product. And that's kind of in some things that we'll talk about a little bit further on here. But ovens, some ovens, and we build a system that's called Profile Guardian. And what that is an independent set of thermocouples that are connected to the edge rails that go down through the furnace. And what they do is they monitor the temperature of the oven. Okay, it's not the control thermocouples. It's not those things. It's another one down at the board level. And what you do is you run a board through, or a series of boards through the oven, and you set a window around the temperature that those thermocouples are seeing. And then if something varies, it'll come back and say, hey, this might be a problem. It's something you need to look at. It's like an independent verification of the performance of how that oven is running during that period of time. If you've got a medical device or some of the real expensive automotive things that are using barcodes, you can tie a barcode in to what those thermocouples are seeing, those independent ones, as that product is going through the oven. That's a good way so that you don't have to come back and profile every time you rerun a product, but you need to run the profile the first time.
Yeah, that makes a lot of sense, Fred.
Yeah, and a lot of people are doing it. Kick made a system. We have one that's built into the oven. Like I said, we call it Profile Guardian. Because it's making sure that the profile isn't changing, or that you don't have another issue. You don't have a fan going out, which doesn't happen anymore now. It used to happen in the past a lot, but those sorts of things. Just the ovens really are doing a lot more to confirm, to guarantee that you've got the profile that you originally wanted. The issue is getting that first one to make sure you know that you're getting the profile that you need.
Yeah, that makes sense. You sent me a slide deck for some highlights of some presentation material. Is there anything on there you want to kind of share with our audience?
We can kind of go through that if you'd like. These are actually slides that came from the basic reflow class that I was teaching at SMTA. Actually, Carl Seelig from AIM was a part of some of these discussions. Carl and I did something. We started off with the basic class, and then the following year we did one with the basic class plus a defect mitigation, and Carl was very helpful for that. So we can quickly walk through some of these. And
I should point out for our listeners who are driving their car and wondering what they're missing. As soon as you get to work or as soon as you get home, just go on YouTube, look up Reliability Matters, and you'll be able to see what we're showing on the video version of this. If you're already on the video version, welcome. If not, be sure and look that up, because this particular episode does have some very interesting slides from Fred. All right, take it away, Fred.
Okay, well, basically, when we were doing this, it was a basic process, and what we did is we talked about, if you go back just to the previous one, here we go. A reflow oven's there to melt the solder, and we need to make a robust solder joint. So, as you've heard us talk about, melting requires that we have to heat that assembly, right? But to do that, to make the robust solder joint, what we need is the correct thermal profile. We flip to the next one. Okay, there you go. It's amazing the number of people that don't understand that there's a difference between the profile in the oven recipe, right? The profile is the thermal process. We'll talk a lot more about that. The recipe is the oven and furnace settings to obtain that profile. You'd be absolutely amazed at the number of times that I'm working with someone that's got an issue, and I say, okay, send me your profile so we can understand what things look like. And they send me the oven recipe. That doesn't help me, because it depends upon the oven, a number of things, how you've had things set up, even upon the weight of the board. Why don't you flip to the next one? Okay, so what's the correct thermal profile? And I think we had as we were going forward earlier. You remember, the objective is to get the best possible results, given the equipment, given the product, and the solder paste. And that really, the solder paste is we've been talking about the profile itself. Okay, the solder paste manufacturer's recommendation is a very good place to start. Carl Seelig was adamant to tell me, yeah, that's a good place to start, but sometimes you have to run outside that recommendation. And normally that's when you're working along with your solder paste manufacturer to identify, really where you should go on that. We go to the next one, please. Okay, so product profiling, and that's really what I'd rather call it than just basic profiling. Okay, it's a way to measure the temperatures, interpret those temperatures of the product going through the oven. It's normally reported, represented in a graph, and sometimes it's even put on a spreadsheet like Excel. But it allows you to know the temperature and exposure time of the places where the thermocouples are installed. Thermocouples, temperature sensors. We go another page, please. There we go. So to obtain profiles, you need a temperature sensor, like I spoke about. You need a data acquisition device. So temperature sensors, we call them thermocouples, right? And they have that thermal process profiler. Okay, so a lot of questions is, what's a thermocouple? Well, this guy, being Tom Seebeck back a few years ago, quite a few years ago, discovered that when he put two dissimilar metals together, they produced a voltage, almost like a little battery. But the properties that are useful for us is that the voltage varies with temperature and it's repeatable. Okay, so with that, then we can identify, by knowing what the voltage is, what we can do is identify the temperature. We go to the next slide. Okay, American National Standard Institute have some official standards for combinations of metals, and they call them things like T, J, E, K, R, S, B, and those are regular. Those are standards. You can go to a table and look up the voltage that comes out of that junction, and it'll tell you which temperature they are. There are some others. There are other types that don't have official standard, but they're used fairly regularly. Things like Platinel and Type N, but usually those are at the higher temperature ranges. But we tend to use the Type K. A lot of our equipment is calibrated for Type K, and the nickel chrome and nickel aluminum is what that is. Those two metals that are put together. Go to the next page, please. Okay. It's important to understand that there are different grades of wire. It's based on the accuracy. You can see the standard limits on Type K is plus or minus 2 degrees C or 0.75% of the reading, whichever is greater, in special limits, which is about half of that. We tend to use special limits. I don't play around with standard limits. Go to the next page, please. Okay, there's a little error cone put together from what that previous slide talked about, and that is below about 300 degrees C, the error between in special limits and standard limits is that plus or minus 2.2 or 1.1. That's lot-to-lot differences, accuracy, not variation within a lot. You can see we were doing some work up at 850 degrees C at one point in time, and boy, we were having an issue where we were trying to get a very, very tight cross-belt uniformity, and when we look at the error of just from thermocouple from lot to lot, we could be as much as plus or minus 3.4 degrees between lots of material. And what we had to do is go back and make sure that we've got thermocouples all from the same lot of material when we did this, just to make sure that we had it tight. In general, plus or minus a half a degree within a lot is what we'll see on a fairly regular basis. If we flip to the next one. The other issue we have to deal with is the aging of thermocouples. We found that at the high temperatures there was a great deal of aging. Thermocouples would become less accurate after 3 or 4 or 5 runs. And I was doing papers at brazing society meetings, etc. And one of the people was involved in SMT, and they said, "Well, what about SMT temperatures?" So we ran a study, and this is from that study. We took 6 thermocouples, put them together at 225 degrees C in air, and ran them down through the furnace. Now, they were from different lots of material, and you can see after that first run that we did, they were within like 1.2 degrees C of each other. The little circle, the red one, were actually 2 thermocouples from the same lot. Okay, so those 2 were one lot, the other one's from different lots. Then what we did is we held the number 6 thermocouple back and ran the 5 thermocouples through a furnace. We were maybe at temperature for half hour, 45 minutes. And after 12 runs, ran them all through the furnace again with the control. And we looked at how they had moved from the control temperature, from the control thermocouple. And you can see there was kind of a question about one of those thermocouples, TC3. It kind of did something weird for us. But again, it was still within that plus or minus 1 degree C of each other. And the other thermocouples, other than number 3, only changed a very small amount. They were basically the same temperature. We repeated that after 23 runs and again after 35 runs. And what it said to us is, probably there is not a lot of aging of type K thermocouples down at 225 degrees C. The real issue that we run into is the breakdown of the insulation. So we'll go to the next slide, please. Okay, so that brings up the discussion of insulation. This is Omega. Okay, they have insulation of Teflon. Kapton is glass, and it's a high temperature glass. You see the designations of TT, KK, GG. Okay. I don't like to run the Teflon thermocouples. The max temperatures you run that on the insulation is about 260 degrees, and that's really close to what we're running on some of the set points in the oven. I see ovens and some of the lead-free up at 270, maybe 265 degrees C. So I don't really like that. The Kapton tape is a little bit better. The one I really like is the glass. I think that gives me a big safety factor because that has a max temperature of that thermocouple of around 480 degrees. And then there's wire sizes you can choose. I like the 30 gauge just because they're a little more robust. Some people like the 36 gauge just because it's a little more responsive. When you get thermocouples, you've got a choice of spool caps or without spool caps. Again, this is from Omega. I like the ones without the spool caps only because they give me more room in the thermal profiler in the insulation package for the thermal profiler. But I also make sure that I use some fiberglass protective sleeving. There's this stuff called, it's fiberglass. It's the Alpha Wire PIF 2400. It's good to over 600 degrees C. And there's a picture to the right there showing you that. That allows you to put things through the oven without it getting tangled in the belt, and etc. I think that's pretty important to do. If we flip to the next one. Okay, thermal profilers. There are all kinds of thermal profilers. There's the kick profilers. I think they're at the SPS now. There's ECD. They're known for the mold. They were very early in the process. A lot of times people will talk about, oh, they're gonna run the mold through the oven. It's sort of like talking about Kleenex when they've got a kick or a data pack. It tends to be a thing that people go back and talk about. The mold is fairly regularly. Data pack has their own, they call it easy oven setup. And then even the Reflow oven manufacturers profilers, and that's basically trailing wires. And we mentioned that earlier. That's where you have long wires that go through the oven. And once they get through the other end of the oven, you either have to pull them through fairly quickly or you pull them back through the oven. On the very high temperature furnaces, what we do is pull them back. We go to the next one, please. Okay, the profiling test vehicle. This is exactly what Tim was talking about. The best test vehicle is the actual product. And I crossed that thing out that says in most cases, because the actual product is the only way to know you have the correct profile of the recipe. The variables are things like mass and the surface area, the thickness, the heat capacity of the material. There's a little formula there that we deal with. Talk a little bit about that in the next slide. Okay, heating and cooling is about transferring BTUs at calories in a controlled manner. I gotta be careful how I say that. I'll leave it there. Okay, Q is the amount of heat being transferred. It can be positive for heating or negative for cooling. The H is the heat capacity of the material. A is the surface area of the product. T is the time, and delta T is the temperature differential between the item being heated and the heat source. As Reflow guys, we have no control over the heat capacity and the surface area of the product. That's given to us. Okay. The only thing we have control of in a Reflow oven is the time and the delta T at the surface. If we go to the next slide, please. Okay. So normally SMT thermal targets are things like peak temperature, time to peak, time above liquidus, soak time, and temperature. Sometimes it's called flux activation by some folks, and then the heating and cooling rates. So basically, we have 6 targets. Okay, if you go to the next slide, please. There we go. On the recipe or the oven settings, we have belt speed, zone set point, and static pressure that we can deal with. Belt speed affects the time. Okay, zone set points, degrees C, and static pressure. It's either control static pressure, inches of water column is the control system that we'll use. Some people have high, medium, and low fan speeds. Some people just run a single fan speed. Those affect the delta T, the temperature differential between the item being heated and the heat source. It's right there on the surface. So what happens is we've got 3 control knobs to try to get 6 targets. And invariably, people that are running Reflow ovens, people are trying to set up the recipes for that, ends up looking like our little guy there with a big sad face, because it's not as easy as you might think it is. If we go to the next one. So how do you mount the TCs? Well, simple. They should be firmly mounted on critical components. Okay, I prefer in the areas you see the circle with the red around it, with the red. I like the aluminum heatsink tape. It's easy to use. It's something that you can put on fairly quickly. If I've got something that I'm going to be using the board over and over again, I'll go to heat-resistant epoxy. The last thing I'll use is Kapton tape. Many times what I'll do is use Kapton tape as is kind of strain relief to help us on the board so that we don't pull things off. And sometimes I'll put an area of Cap-10 tape over the aluminum heatsink tape and to press it down to make sure it stays down. There are some people that like to take the aluminum tape and kind of use the Cap-10 tape and make it like a window around it, just so they help it keep it down. The first time you run the board with the aluminum tape, it'll stay stuck down pretty well, but after it comes out, you really need to push it back down with your finger just to make sure it stays in contact. If we go to the next slide.
Before we do that, Tim, I have a question for you. How many times in your career have you responded to a customer issue and they swore the profiling was absolutely perfect the way you suggested it, and then you went to inspect their profiling method and found out, the thermocouples were attached with peanut butter or something?
Well, define perfect, right? So I'm following your recommendation is often what we'll hear, and what by that they mean, they've tried to match up our online recommendations or our published recommendations. And you have to understand, our recommendations are written very broadly. We have to accommodate people that have a 5-zone tabletop oven and people that have a 13-zone nitrogen inerted oven. And so the Reflow profile guidelines are written to try and accommodate all of the equipment that's out there. So yes, Mr. Customer, it does fit into the box, but it doesn't mean that it's optimized for your assembly. And that's where having a vendor that can communicate to you and work with you on developing a profile, really training your personnel that are responsible for it in the strategies that will help them generally, and then more targeted assistance to our product's preferences. That's where this, it's a bit cliche to say, we give the best support, but it's particularly in the area of profiling where our support gives the best result. So that happens a lot where they say we're in the window, and you are, but it's just not your window to give you the outcome that you want. You meet the letter of the law, and then the other thing that's very common is that profiling libraries will be evolved to basically small, medium, and large. So it's the 80-20 rule. 80% of the boards that they're building run through 20% of the profiles that they use. They have a couple that they run. Oh, this board's big, so we run it a little slower and a little hotter. This board's small, so we run it a little faster and a little lighter. Logic doesn't necessarily dictate how a profile responds to oven inputs. You think it's going to do this, but until you measure it, you don't really know. So you have to profile, as Fred has emphasized, with the assembly that you're actually working with. And here's another scenario that's common is personnel changes will lead to a loss of tribal knowledge on profiling. So a guy who was, an operator who was present at the time of the oven install will get trained by the oven installer and understand what it is that they need to do. And then they will go on to a new position or a new career. And the guy or person that replaces them never really understands profiling. And so everything becomes very static. And it has happened to me couldn't count on my fingers and toes the number of times I've heard, well, that's the profile that they gave us when they set it up. And that's it. Like nothing ever changed. And luckily for them, the mix of boards that they have were able to fit into that profile. Oven technology has evolved to where these things are pretty good at accommodating a lot of different variables. But we get the call when things fall outside of that window. And that's where we start to unravel a lot of these practices that are suboptimal.
I'm putting the DVD player on my record player, and it won't play. I'm not getting any sound.
Isn't quite that bad, but it's just more along the lines of you see a profiler sitting on the corner, and it's covered in dust. And we're like, have you used that recently? Nah, the guy who knew how to use it, he left, and they never really trained me on how to use it. So
Yeah.
Everything's been fine up until now, but now I've got this new board and it's not soldering properly.
Yeah, it's a land
got an issue.
It's a land where time stood still. It's a throwback in some cases. We see that in the cleaning business. I'm sure every part of our industry has that. Fred, I'm going to turn this back to you.
One of the questions comes, where should you put the TCs? We know how to mount them. We've got some ideas doing it. And usually I say, okay, you really want to put them on the big component, a small component, and a critical component. Sometimes you want to put them on the board surface. There are times where you want to put it in the left or the right side of the board, the front or the back, because sometimes ovens do not have very good uniformity. So that's where you should put TCs. That leaves a lot of places, doesn't it? Okay, the next slide. Okay. Part of where should you put TCs? It really needs to go where you think that's important or where you're having a problem. On the legs of components, on big connectors, the center of BGAs, on the ends of small components, on the component surfaces, on the board surfaces, on capacitors legs, on relays. That's kind of where things should go. That's only a small portion. Okay, if we go to the next one, please. Okay, but don't do this. You see that thermocouple there on the left? That thermocouple was actually put on with solder, and it's sticking up out of the solder. It's sitting up in the air, where the other one's right down on that board surface or on the surface of that leg. If you go to the next slide, please. Okay, the one on the left has things that are mounted correctly. This was epoxy, mounted them right down on the board surfaces. The one on the right had them on the surface of the epoxy. They didn't embed them deep enough. You can see every little orifice hole and every little orifice and the effect of every little orifice hole in the orifice plates. I'll get that right sooner or later. Okay, so if you go to the next one. This one was actually handed to me by Carl Seelig, and he said, "Look at this, Fred." He said, "What do you think of that red one?" And I had to look at it a couple of seconds and say, "Yep, you know what's going on." The red line is one that probably was up on the surface, and the thing that really gave it away was how jagged it was during the cooling, because you could see every little hole in the orifice plate. It led the other ones as it went up in temperature. It was a little bit higher in temperature because it wasn't down against against the product. Okay. Sometimes we get questions how do you choose the first recipe? You've got a brand new board that comes up, and you say, gee, where do I start? Well, basically you can use your knowledge and experience. Many of the oven manufacturers have default recipes built in. Ours have a simple ramp to spike lead-free recipe, and it has a ramp soak spike recipe. Generally, it was used on the tin lead, eutectic tin lead. In our particular case, they were done with very heavy boards. So if I'm using our default recipe, I'll usually take about 10 degrees out of all the set points and start there, because it's easier to heat an oven than it is to cool them. One thing that people use is a recipe from a product that's close to the same size. But again, we really talk about having to go back and do profiling when you've got a new board. Some of the Reflow profiler people have predictive software that help them to get started. We have something built in our oven called Recipe Pro, where you put in basically the loading of the board, the thickness of the board, whether it's got a lot of components in it or a small number of components in it, and then you go through a couple of steps, and it'll come back and give you a recommended starting recipe and put that in. But even after you do that, you need to make sure you profile, because you really don't know until you've got that profile done right. Oh, the other thing you do is you call somebody like BTU and say, Fred, do it. And that happens every once in a great while. Can we step to the next one? Okay, so there's a procedure that you really need to do. You run a recipe that you set up, one that you guess or something that you've got some experience with, and you wait for the oven to stabilize. It doesn't do any good if the oven isn't stable. You, at that point in time, identify or set the process window that you want. Again, the paste manufacturing specification is a good place to start, or the process window that you desire. Then you run the board and the profiler through the oven and obtain the profile data. Then you change the oven recipe if it's needed. You can change the set points, the belt speed, and the static pressure. Then you need to rerun it and confirm whether it's correct or not. And if you need to, then you repeat it. We go to the next slide. The question is, how do you decide what to change? Again, you use your knowledge and experience. The predictive software does a real good job at helping you to get close to that. And again, you have somebody else do it. Or you can go and grab an article, magazine article that was done in circuits assembly in 2009. Boy, that was a long time ago. And it was one called the Oven Adjustment Effects on the Solder Reflow Profile. In 2009, it was actually the highest downloaded article that they had ever had. It was a very, very interesting one to see they did that. And actually, in 2010, it almost beat the 2009 number. Okay, we go one more profile, one more. Okay, this is predictive software. KIC uses something called PWI, Process Window Index. And what it does is if you can get it to 0, you're right in the center of the process window. And this is what KIC came up with. They said that, oh boy, you can get to about 19%. You're a lot closer to the center if you run their recommendation. And down near the bottom of that that slide, there were two lines of things that go across. One is the set point that was done during that profile. The one below that is the setting on its prediction. And if you run the prediction, it may not end up being exactly at 19%, but it will be better than the 70%. Okay, that's all for this one.
You are, we've made you breathless. It's like you've just run a marathon.
Oh, wow. Yeah, I have to have more coffee is what it is.
Yeah. Well, that's a year into the pandemic. We're tired just sitting in front of a computer now because we're not.
That's it.
Atrophy's all built in. Well, that excellent presentation. Thank you, Fred, and thank you, Tim. Is there any? Are there any parting thoughts you'd like our audience to hear on the subjects we've been talking about over the last 2 weeks?
I would just say, Fred, great job. I think I would agree with everything that you've proposed. It's exactly correct information, and I think that the timeline that you gave or the instructions that you gave in terms of how to collect a proper profile reinforce what I was saying about why it gets done infrequently. It's arduous, and I don't think there's a way around it. And it just is the importance of it in terms of product quality and data collection and retention. It can't be overstated. You just have to do it. It has to be budgeted into your workflow. And one thing on these PWIs, they are a source of frustration for manufacturer for us is when we're giving support to our customers, because the customer ends up becoming so focused on hitting that 0 that they lose sight of the fact that the job here is to create a good solder joint. And so that is the tool should not dictate the process. It should be used to aid the process. So, and it, I think it has a lot to do with a lack of understanding of training of the software capabilities and how to manipulate it by the users. And that can be frustration for us when we try to provide support, because we'll give guidance and say, okay, this is what you need to do. This board's thermally massive. You're going to have to run a 4.5 minute profile. And they say, no, but I'm outside of the PWI. I can't do that. Well, no, look at the solder joint I just made. It's perfect. Yes, but it's outside of the PWI. My quality manager will kill me. And so it's something we've had to try and overcome. We would just ask for the customer's understanding that the goal here is product quality, not adherence to the recommendations of a piece of software.
right? I used to fly airplanes. I'm a licensed pilot. Although I'm not current anymore. Don't chase the needle is what my instructor.
Don't chase the needle. Yeah, I was going to actually use that as an analogy, not thinking it was it, but yeah, to a certain extent, you have to believe your instrumentation. But on the other hand, if you're looking out the window, he's like,
yeah. Well, they teach you scanning, right, left to right, all the gauges. But yeah, in the early days of flying, the controller says they want you at 6,000 feet. So I'm looking down, literally looking down, doing this, trying to keep the plane not 1 foot higher, not 1 foot lower. And it really is, yeah, when they say 6,000, they mean 6,000, but they don't care if it's 6,001 or 59.99, right? I mean, I totally appreciate that point of, the PWI is your general plan, but the destination is what's important. The outcome of the solder joint is what's important. If it strays a little bit here and there, depending upon the application, one can stray a little more than others. But don't throw away a perfectly good board just because you were a couple degrees out from the
right.
The target.
Quality might not understand that. A process engineer will understand it, but a quality manager might say, "Oh, but the box is green, the box is red."
Yeah.
Right.
So, yeah. The IPC-610H is what we are. That is the quality manual. That is what we are striving to achieve, whatever the objective is, as per those results. Everything else is noise.
Yeah, that's some valuable noise. Kind of direction arrows rather than
direction arrows. Yeah.
That makes sense.
One of the other things that you can do with the Kick software is that you can put different process windows on the same board for the different thermocouples. It has the ability to go in and do that. So if you've got, some component on the board that doesn't run to whatever that normal process window is, you can put a different process window on it. And the
point is that knowledge gets lost by the time it makes its way down to the person that's actually running the profiler. That's understanding the software at a fairly sophisticated level.
Yeah, that makes a lot of sense.
What you're talking about is something like we end up with over in China a great deal. Somebody will sit there and you'll go and show them how to run a particular process, and we'll set it up and we'll say, but this is why you do that, and this is why you do this. And they don't care why. All they want to know is what number to set it at, so that they're not responsible beyond the number.
For what happens, yeah.
We see that.
I did what I was told.
Push the blue button. Push the blue button, and I totally get that. Did what you said.
Yeah.
So, gentlemen, you guys are, as always, a wealth of knowledge. Tim, it's great to see you again, and Fred, it's great to see you again.
Great.
I will put Tim and Fred's contact information on the show notes. So if you are listening to this on Spreaker.com, that's who hosts the show, Spreaker.com. The show notes are available there. And there's also contact information if you're watching this on our YouTube channel, the video version. There'll be contact information there. And I know that Tim and Fred will be anxiously sitting by their computer, by their email program, looking for your questions and anxious to answer them. So feel free to contact them 24 hours a day. They don't mind. How's that?
Anything we can do to help.
Anything you can do to help. All right, guys. Well, thank you so much. It's been 2 fun-filled episodes of jam-filled facts and figures and best practice suggestions, and I hope our audience finds this information. I'm confident they'll find this information very helpful, quite beneficial. Thanks for sharing your knowledge, and I hope to see you again physically at some future event in the far, far, far future, in a galaxy far, far away, when we get out of this pandemic. But in the meantime, we'll have to settle for seeing your face on my monitor. Again, gentlemen, thank you so much. I really appreciate you being here.
Thank you, Mike.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, or virtually wherever you get your podcasts. A special thanks to Circuits Assembly Magazine's PCB Chat at PCBchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks for your questions and episode suggestions. Please keep them coming. Send them right down here to my email address. Once again, thanks for listening. Stay safe, stay healthy, and stay happy, and perhaps most importantly, keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.